Hello, everyone, and thank you for coming to this talk. Thank you for the introduction. My name is Nikola, and 2 talks away, we heard about how to model novice text entry performance, and now I want to take us back and revisit some of these expert text entry models. Now, expert text entry models allow us to estimate how fast somebody can type on a given keyboard, and this helps us evaluate not just existing keyboards, but also novel keyboards that we are creating. One observation, though, is that these kinds of upper bounds on expert text entry are also significantly overestimating the empirical speeds that we are able to observe, even when we recruit expert typists. And what this means is that we are overly confident or overly optimistic about how fast we can actually type on some of these new keyboards. And in this talk, I actually want to show you how we can compute even a tighter bound on expert text entry by simply considering the changes in people's behaviors, their typing behaviors, in response to costly typing errors. Now, when people are typing on their mobile devices, inevitably, they will make an error. And when they do make an error, they have to go back, press on the delete key to delete the wrong character, and now target and select the correct character. And this is a typing error that takes time. Now, previous research tells us that people change their pointing behavior in response to these kinds of costly errors. They decrease their movement time in order to avoid making errors and avoid incurring these kinds of costly errors. So that is why we then hypothesized that the same thing applies to typing tasks where the user points to different keys. And before I actually show you how to compute this model, I want to persuade you that this kind of phenomenon translates from pointing tasks into these more specialized text entry pointing tasks. So what we've done in this work is we try to simulate a text entry task by providing participants with a mini QWERTY layout, the standard layout on Android devices. But what we did is we simply removed all of the letters from the keyboard. And we asked participants to then click between all of the pairs of the keys on the keyboard repeatedly. And we measured how fast they were pointing between these keys. Now, we had 2 different conditions. So when the user, or when the participant, would miss a target, we had a riskless condition, where the participant would just continue on to select the next target. And this is trying to simulate what the existing models are doing when trying to estimate this upper bound expert text entry speed. And then we had a costly condition in which participants actually had to go back to where the delete key would have been, select that delete key to simulate deletion of this wrong character, and then go back to press on the correct key. And we did not let them move to the next trial until they performed it correctly, and they performed correct target selection. Now, we had 20 participants who completed 1,200 train trials and just over 4,300 test trials each, which were split over 6 blocks. And they selected targets with their thumb on their right hand. All of them were right-handed. And what we were able to observe is that they changed their error-free movement time. This is important. This is not just movement time that includes the error. This is their error-free movement time in response to these costly errors. And they did this to reduce their error rate. Now, if we use this information, now, these values, these movement times, to compute how fast they would have typed on a mini QWERTY on Android, we would find that they would type 2.4 words per minute slower in the costly condition. So here we demonstrated a measurable difference in movement speed caused by this cost of error, but there is no existing model of expert text entry that accounts for these kinds of changes in people's behaviors. These kinds of existing models first take the movement time between any 2 characters, and then they try to estimate the time it takes to to type all the words or any given word on this keyboard by considering the movement times between consecutive characters, and then use that information to compute how long it would take to enter all of the words in some corpus, let's say of English language. And now we can use that information to calculate the mean speed for entering any character on this keyboard, which gives us an ability to estimate the speed of entering any word on the text entry speed on this keyboard. And the challenge here is that at the very beginning, we have this movement time that does not consider the changes in pointing behavior in response to costly errors. So what we provide is an expert text entry model that can calculate this upper bound on text entry speed by considering these changes in pointing behavior. And the way we do that is we base our work on previous paper in which we showed how people point at targets in general in response to these costly errors, where we calculate the optimal total selection time for any target by considering the movement time, the optimal movement time that allows the participant or users to reduce the probability of error to incur the costly pointing error C. Now, in these text entry tasks, this particular error looks like this. When the user is entering some text, the user will inevitably make an error, and then the user has to go and point to the delete key, which incurs completion time to select delete key, and then the user has to go back and select the correct key, which incurs the penalty of that is equal to the completion time of selecting the right character moving from the delete key. So now we can express that cost, but also we can calculate the upper bound on the cost of moving to the delete key, in which we consider the movement time, the costly movement time to the delete key, but also this parameter, which we call C-tap, which is any additional taps that the user might have to press on the delete key because of making these continuous error and entering more characters while trying to press on the delete. And now with this, we can solve this optimization problem to estimate the optimal key selection completion time. And then we can go back to the existing models and consider now the error-free movement time that has been adjusted for the effect of these kinds of costly errors, and compute the upper bound text entry speed. Now, the earlier study that you saw empirically measured these movement times between different keys, but that is challenging because it takes a lot of time to collect this kind of data and may even require expert typists. So instead, we use the existing pointing task parameters to estimate our movement times, both the costly ones and the riskless ones. And once we perform this optimization, now we can compute 3 different upper bounds. One that is simply based on Fitts law, the pointing task. One that is based on ffit, that takes into account the behaviors of pointing with a finger on a touchscreen device, and our costly upper bound. And what we are saying is that our upper bound is the lowest one, but we still need to show that it actually represents an upper bound on empirical text entry. So what we did here is we ran a text entry study on a standard Android Mini QWERTY keyboard, and we use the standard McKenzie dataset that you heard about in the previous talk. And we asked participants to simply transcribe the phrases that they're able to see on their phones. Now, we recruited 20 participants from the original study, which we call the training set, the participants whose behaviors we have already seen, and we base some decisions based on their behaviors. And 8 new participants, which we call the validation set, which we have not seen before. And all of these were expert typists with years of experience typing on these kind of mini QWERTY keyboards. For all of them, we again asked them to enter text only using their thumb on their right hand, and all of them were right-handed. And all of the participants completed 5 20-minute sessions, where sessions were at least 2 hours apart or at most 2 days apart. And participants on average transcribed 350 phrases each, which gave us a total of close to 7,500 phrases in the training group and over 2,700 phrases in the validation group. And now we can compute the empirically estimated speeds for the training group and for the validation group. And what we're able to see here is that our costly model offers a tighter bound on expert text entry speed than these traditional models. And what's also interesting is that we were able to improve the accuracy of this upper bound by 3.29 words per minute compared to the best existing model, which is based on F-fits. Now, when we look at these differences between the upper bounds and the empirical speeds, we can now estimate the effect of the risk aversion on people's text entry task. And what we found that risk aversion accounts for at least 65.98% of the difference between the best existing model and the empirical speeds that we were able to measure. So here we provide a framework to estimate this tighter upper bound on expert text entry. And we also provided the empirical evidence to show that this actually is an upper bound. We could have overshoot and provided something that is not an upper bound, right? But what's also important is that we've shown that the aversion to these costly errors explains most of the difference between these existing models and the experimental speeds. And the remaining difference then is probably due to some of the other factors, which I will discuss in a moment. And what's important is that we show that lowering cost of error can help increase the overall text entry speed for any keyboard. And that's why this also has implications for different optimization methods that we have today that include the speed and the accuracy of text entry, where now it may become important to put some of the characters closer to the delete key, some of the frequent characters, so that if the typist makes an error, the typist can correct that error a lot quicker. So for the future direction, there's a lot of different implications. One of the things is that we are still looking only at the thumb text entry here, and we're looking at the Android Mini QWERTY keyboards. And we did that with purpose, because we wanted to make sure that we eliminate a lot of variance and hold a lot of these other factors constant. But we still would like to take a look and see how different keyboards, different modalities, different ways to hold a keyboard, or different ways to enter text can impact the speed of text entry, now considering the cost of error. Now, of course, there are other different variables that we want to take a look at. So we're still looking at the motor performance in expert text entry. But the remaining difference that we are observing between the empirical speeds and the upper bound that we estimated could be due to factors such as cognitive load, maybe visual search, which may not be as important in expert text entry tasks, but should probably be considered. And of course, there are implications for design and evaluation of future keyboards, for the future autocorrection features, because these are the kinds of features that now help reduce the error cost of text entry. And for future work, we intend to look at how different autocorrection features and the trust that users have in these features impact people's text entry behavior. Thank you.
Thanks for your talk. I was going to suggest the visual search, so thanks for citing me
I'm
already.
sorry?
I was going to suggest visual search as a factor in the bound, but you already cited me. But another factor could be attention. In order to detect an error, you have to move your eyes to the text entry area instead of the keyboard, and at that time you're not able to type as well. Even with experts, you really need to guide your finger with your attention and with your vision, and you need visual search there. So that's something that probably affects a lot of your typing speed. But it becomes really difficult at that point because you have different strategies. You can proofread often, but it takes time. But if you proofread very rarely, then you might have to backspace a lot. So there is a certain optimum strategy given your amount of errors that you make during your typing. So it's a really interesting problem, but I agree with you that it's an optimization problem. You just need to find the best strategy given the bounds that we have.
Right. No, thank you for that comment. And yes, that is very important because right now we're doing everything we can, even in the design of our empirical studies, to eliminate a lot of the, especially when it comes to expert text entry, to eliminate a lot of these variables. So we're using a transcription task versus a composition task, right? That completely changes how somebody will type. And we know the implicit rate of text entry and what it is and why we're seeking to reach it and so on. And this work is one step towards exploring a new parameter. Your work is amazing in a sense that it's now saying it's not just the motor components. We need to look at the cognitive level components as well and have a complete picture. And then to add to that, work by Arif Ahmed, who's looking at the actual way that people correct errors, also puts this into a whole picture. And one day, I think we're going to have very accurate models of how people actually type to the point where maybe we're not even going to be bringing in people into the user studies to evaluate them.
Quick comment. I obviously am very excited about combining the papers in this session, especially a simple comparison between what you found here on the two key comparison versus the clarity stuff on the previous paper.
Right.
And of course, for my own work with Caitlin on passive haptic learning, we would love to then see how our passive training affects all this. It seems like a very exciting time.
Yeah. Thank you so much. Yeah, these are all of the different parameters we just have to keep considering to really have very accurate models of how people actually type. So it's a great point, and it's not just even how people type, but how we design the task to estimate the expert text entry performance.
Maybe we can start to get an online forum with some data sets, then keep on sharing these results, because I think there's a lot of stuff from the papers I saw today that would benefit a lot of us in this field.
Yeah, we should do that and start compiling more of this information into a centralized location. Thank you for the comment.
I should have a quick comment. I feel in the real text entry, we have this auto-correction feature. So some user might adopt this riskless condition. They will trust the auto-correction and then they will just move ahead and won't correct intermediate errors. But some users might use this costly strategy. They will correct every mistake. So I think it's very likely that what we really observe in the real world is something between these two curves, the real performance. Yeah.
This is a very good point, and maybe just to try to rephrase it, there are different error correction strategies that may affect how people change their behavior or how the final empirical speed is derived from that. But one of the things that we've decided to do in this work is sort of look at this most immediate realization that an error has been made or that the user has made an error, because we believe that that is the kind of error that will affect the error-free movement time for this user. So our focus here was more on the effects of the error-free movement time and how it adjusts possibly over time. But to really, again, go back and now say, how does the time to correct the error impact the actual expected mean text entry speed? It's going to be very important to include that parameter as well.
Excellent. Thank you.
Yeah, thank you.
So let's thank Nikola for the great talk.
Thank you.